Welcome to an introductory course into EUV optics. My name is Sascha Megura and I work as a system engineer for ZEISS Semiconductor Manufacturing Technologies. This presentation will cover the EUV development over the last 35 years. Several companies have built EUV optical systems, but I will mainly focus on the optical systems built by ZEISS. At the core, this presentation is about resolution. The concept of resolution also plays a fundamental role in the world of microscopes. The theory of optical imaging was investigated by Ernst Abbe. His theory expresses the resolution limit of a microscope as d equals lambda over 2n times sine of alpha, where d is the minimum resolvable distance of two lines, lambda the wavelength, and n is the refractive index below the last lens element. Alpha is the opening angle of the light cone on object side. Today, Abbe's formula is used in optical lithography in the form resolution equals K1 times lambda over NA. K1 is the process factor and a measure for the capability of the manufacturing process. NA is the numerical aperture and describes the opening of the light cone at the wafer. EUV lithography changes the wavelength lambda to 13.5 nanometers, an order of magnitude less compared to the wavelength of current deep UV ARF immersion optics. Within the EUV wavelength, the NA can be increased step by step, and K1 can be reduced. With all these three knobs, we are able to reduce the resolution and continue Moore's law. And also the other way around is true. Moore's law is driving the requirements on the optical system. During the last decades, a new exposure wavelength has been introduced a few times to continuously improve the resolution. It started in the early 80s with the so-called G line of the mercury lamp and went from I line to KRF and ARF. Within a given wavelength, the NA was increased from product to product and K1 lowered. Shown are the optical lenses with the highest NA within a given wavelength. Around 2006, the transition to immersion optics can be seen. From 2012 on, EUV lithography continues improving the resolution with the product NXE 3400. The 3400 optics features an NA of 0.33 and is the current solution for high volume manufacturing. The high NA optics will have an NA of 0.55 and is planned to be shipped around 23. Regarding the optical system, the short wavelength of 13.5 nanometer imposes several demanding boundary conditions. Firstly, EUV light is strongly absorbed by all materials and gases. Therefore, the whole system must be operated under vacuum. It also implies that all optical elements, including the mask, must be mirrors. Secondly, the refractive index of all materials at 13.5 nanometer is very close to 1, so stacks of multilayers as Bragg reflectors had been found as a solution for the mirror coatings. Thirdly, the optical constants of coating materials limit the mirror reflectivity to a practical maximum of around 70%. The design of a high transmission EUV optical system must therefore minimize the number of mirrors, achieved most effectively by using A-spheres. And producing A-spheres is particularly challenging in terms of optics technology. These boundary conditions determine the layout for the optical train. The EUV optical system consists of the following optical modules: the collector of the source, the illuminator, the mask or reticle, and the projection optics. The EUV light is generated by a plasma source and is collected and focused by a collector onto the entrance of the illuminator, the so-called intermediate focus. The illuminator then forms the light such that the mask is illuminated very homogeneously from well-defined beam directions. The mask is a critical optical element in itself. The structures on the mask generate a complex diffraction pattern containing the circuit information. The projection optics catches and recombines this diffraction pattern, finally imaging the mask structure onto the wafer via the numerical aperture. In 1984, Professor Kinoshita from Japan began to consider seriously X-ray reduction lithography. The graphic shows the configuration of the very first experimental setup in Tsukuba, Japan. From left, synchrotron radiation is coming, and the mask was a transparent silicon stencil. 2 X-ray mirrors were used for imaging. The alignment accuracy of the imaging system mirrors was very poor because the alignment was carried out with a visible microscope, and all of the replicated patterns were severely distorted. An image of a 4 micrometer line and a space pattern was finally produced in 1985, and the results of the early experiments were first presented at the annual meeting of the Japan Society of Applied Physics in 1986. Unfortunately, the response to the paper was rather negative. The audience seemed unwilling to believe that an image had actually been made by bending X-rays. After Kinoshita proposed soft X-ray lithography in 1985, first efforts towards realization were initiated in Japan, the USA, and the Netherlands. During the following years, several optical systems with low NAs of up to 0.1 were designed and realized. EUVL development at ZEISS started in the mid-90s. Under the first European EUV program, the first EUV workshop organized by ZEISS was held on November 13th and 14th, 1995 at the location of ZEISS headquarters in Oberkochen, Germany. With participants from the EU and the US, this workshop started the feasibility study for the development and production of EUV optics at ZEISS and its partners. On the part of ZEISS, the studies included optical designs for the projection optics and the illuminator to derive technological requirements. The activities also included the manufacturing and the metrology of aspheric surfaces. In 1998, the lithography community was in search for what should come after ARF, the so-called next-generation lithography. For EUV, Sematech's NGL task force listed full-field optical design as the critical issue number 1 for EUV in December 1998. Although on paper optical designs were available, it was unclear if the requirements, especially regarding flare, could be met during manufacturing. Over a period of only 3.5 years, from November 1997 to August 2001, the topic optics matured from the status potential showstopper to solution anticipated. A significant step was achieved in 1999 with the fabrication of mirror ELT M2 for projection optics designed by the Corning Tropel Corporation. As an object for technology comparison, very good surface errors were achieved and appreciated as a major breakthrough in optics manufacturing. The figure quality of 0.14 nanometer surface RMS on a 1.8 micrometer aspheric zero-dur substrate was measured with an in-house interferometer at ZEISS. The MSFR quality was 0.12 nanometer RMS on a spherical zero-dur substrate with a square field of 300 micrometers. The HSFR quality was 0.12 nanometer RMS on a spherical zero-dur substrate with a field of a square 1 micrometer. Since mid-99, ZEISS then started to build the optics for a small field tool, the so-called MET. The MET was finalized in 2003. MET stands for Micro Exposure Tool, and it has its name because of the small field of 200 micrometers times 600 micrometers. The MET was built in cooperation with Lawrence Livermore National Lab and Lawrence Berkeley National Laboratories and has an NA of 0.3 and a magnification of 5x. The system consists of 2 mirrors. based on the concept of nearly equal radii of curvature. The optics features a central obscuration. A small hole can be seen in the top mirror. By applying a surface interferometry and polishing with a repeatability of 60 picometers, mirror figure and roughness values from 0.2 to 0.3 nanometers were achieved end of 2000. In mid-2001, coating of the mirrors and assembly of the first MET was completed at the National Lab. In the beginning, Zeiss fabricated the aspheric optical surfaces for 2 systems. The first MET was delivered to Zeiss for further testing of the aerial images and resist prints at Bessey in Berlin. A beamline was set up specifically for research purposes at EUV wavelength using a synchrotron light source. Aerial image metrology qualified the final performance of the optical system and was based on the detection of 3-dimensional intensity distributions of imaged mask patterns. One of the first images printed with the MET at EUV wavelength was taken at Bessey in November 2001 and is depicted here. The photographs show structures consisting of single lines and grouped lines, arranged in different orientations. Going through focus, astigmatism, coma, and spherical aberration could be determined. On the left picture, test structures with 100 nanometer line width can be seen, and the grouped lines are blurred but still resolved. On the next picture, you can see that the pattern with 70 nanometer line width could not be resolved. In addition to the aerial image measurement, an interferometer-based metrology machine was installed at Bessey in 2001. Its purpose was to show to what extent the deep UV proven shearing interferometer principle could also be applied to EUV. The picture on the right shows one of the first interferograms at EUV wavelength imaged in November 2002. A structured transmission mask was used where a diffraction grating divides the incoming waves. Their superposition generates interference patterns which are registered by a detector system. Some series had been taken in various focus positions, finally proving the feasibility of the principle. In the following years, the resolution capability of the MET could be improved down to 20 nanometer half pitch. The MET has mainly been used for photoresist and mask testing. As a small field tool, the MET did not allow for systematic study of field-dependent imaging effects like flare or chief ray angle rotation. Therefore, ASML and Zeiss continued their EUV development with the introduction of their first full-field R&D EUV system, capable of exposing a full field at wafer. The name of the prototype was Alpha Demo Tool, or ADT, and was delivered for the first time in 2006. Here you see the Alpha Demo Tool inside the system metrology stand in 2004. Compared to the MET, the Alpha Demo Tool has 6 mirrors inside, and its height is that of a normal person. System metrology for the projection optics is a key building block in the manufacturing. Its purpose is twofold. Firstly, system metrology is used for final system qualification, and secondly, it is used for feedback loops in system adjustment during the system integration. A key point is the selection of the operating wavelength of the system metrology. The simulation of the ADT projection optics and the alignment processes predicted that a metrology at the EUV wavelength was not necessary. The expected differences to the established metrology at 248 nanometers were correctable within the scanner. The Alpha Demo Tool metrology stand includes interferometer and aerial image metrology, both at 248 nanometer wavelength. 2 optic sets for Alpha Demo tools were produced and shipped. One ADT was shipped to Zematec in Albany, USA, and the other ADT to IMEC in Leuven, Belgium. The IMEC ADT passed its site acceptance test in 2008. Dense lines and spaces with half pitches ranging from 35 to 30 nanometer could be printed. At IMEC, as well as at Zematec, the Alpha Demo Tool was part of an integrated process line. First functional devices were produced in Albany in 2008, the SRAM cell of an AMD Typhoon full chip layout being printed. A 22nm SRAM cell was demonstrated by IMEC in 2009. These results proved that EUV patterning can indeed be integrated into a semiconductor production flow. The alpha demo tool allowed significant learning on EUV patterning. For instance, shadowing effects and their full field dependency were studied. An additional effect is related to flare. Since the mask shows brighter and darker regions, the resulting flare at wafer will be field dependent, inducing field dependent imaging effects. As a systematic effect, this can be compensated based on the flare distribution of the optics. It was on the alpha demo tool that the feasibility of field-dependent OPC for shadowing and flare correction was proven for the first time. The alpha demo tool allowed to gather first experiences with EUV lithography processes in an open, pre-competitive R&D environment. The alpha demo tool at IMEC remained active until 2011, then being replaced by the NXE 3100. Learning from the prototype tools was essential for improving core optics technologies like mirror polishing. These improvements were realized in the successor of the alpha demo tool optics, the Starlit 3100. The first shipment of the scanner NXE 3100 was early in 2010. Shown are the optical modules for the 3100. Left the illuminator, right the projection optics. The layout for the projection optics remained the same, consequently the NA of 0.25. The full field size and the magnification of 4x remained unchanged. Following the alpha demo tool, ASML built a high-volume serial production platform for EUV named NXE. The NXE 3100 scanners were installed directly at the chipmakers' sites. As mentioned earlier, flare was originally rated as the most critical issue for EUV optics. The source of flare is scattering of EUV light from the roughness of the mirror surfaces. The alpha demo tool exhibited a flare level of 16%. This high flare level, together with the aberrations, led to concerns regarding the image contrast. Therefore, a general target of a flare of below 8% was set. The 3100 generation was shipped to chipmakers and research organizations with flare values below 6%, clearly below the original flare target. A reduction of flare by a factor of 3 was therefore achieved within the years from 2004 to 2008. All these systems, the MET, the alpha demo tool and the Starlit 3100, provided an essential learning curve for what was coming next, namely the Starlit 3300 and 3400 family. The Starlit 3300 is the first EUV lithography optics that has been developed for serial production. In the next video, we will have a closer look at this EUV system, which is the only optical system for EUV that is presently used for the high-volume manufacturing of chips. Thank you for watching and see you in the next video.